Welcome to the second session here at A4. And now it's going to talk about streams and Akka Streams in particular. Welcome, Johan Andrén.
Thank you. So it's really great to see that 1.5 million people came here just to see me. I feel really good about this. So are you ready for some really, some blast beats and some really loud music? Yes. Yeah, sorry, there will be no such thing. We're going to talk about Akka Streams. I'm very sorry to make you disappointed, but I had to kind of make something to draw people in. So I work at Lightbend in the Akka team as a developer. We're six people employed by Lightbend. And I have been working on the JVM since 2005 maybe, based here in Stockholm. Så jag talar utmärkt svenska. I'm also co-organizer of the Scala user group here in Stockholm, and we have meetings, monthly meetings, about-ish, interesting speakers talking about Scala stuff. Yeah, Akka. How many of you have heard of Akka before? Okay, that's basically everyone, almost. Cool. So Akka is a toolkit that is meant to make building concurrent and distributed systems simple, for some meaning of the word simple. And at its core is the actor model, which is basically a way to, instead of using threads and locks to do concurrency, we do message-driven applications. So this makes it possible to write concurrent stuff without having to bother with synchronized and stuff like that. In the toolkit is a bunch of things. So it's the actors, which is like the core module. We have cluster, which makes it possible to take your application which you built that runs locally and actually move actors out onto a cluster and scale out or get resiliency. For example, you would have 5 nodes and one server can crash and your actors will kind of move over to the other nodes in your cluster, so to keep high availability, for example. We have persistence, which is event sourcing on top of actors, and we have an HTTP server. Very soon we also have an HTTP2 server. So 2 guys in my team have been working on that since late fall. We also have some integration with the latest buzzword things that everyone thinks they need to use in their systems, which is Cassandra and DynamoDB and Kafka, which might be really good technologies, but how the IT business is. It kind of everyone jumps on something when a big enough player says that they do something, everyone else want to do it. And we have streams, which is what I'm going to talk about today. Before I start talking about Akka Streams, I'm going to talk a bit about Reactive Streams. So how many of you have heard of Reactive Streams? Okay, also quite a lot. So I guess we can move through this pretty quickly then. October 2013, Roland Kuhn, who was the tech lead in the Akka team at that point, and Eric Meyer, who is this very colorful person who was, at that time, I'm not sure he's involved anymore, involved in RX. They were doing this training materials on Coursera, like a Scala training materials or Reactive. And they ended up in a discussion about asynchronous streaming of data. And we had some needs inside of Lightbend that we had solved in different ways. So we had one way to solve it in Akka with Akka.io, which is NAC-based. And we had iteratees in play, which was a concept from Haskell, and a lot of people didn't really grasp it, and it was almost impossible to write a Java API for it. So they kind of ended up forming this Reactive Streams expert group together with some more people. Twitter, think Pivotal may have been in there also in the beginning, not sure. And they made this specification and a TCK. TCK means a technology compatibility kit, I think. So it's basically a test suite to verify that you implement a specification, right? So we have the specification, which is a set of rules, and then we have the test kit, which kind of verifies that you have done it right. And in 2015, this was released. And then I think currently, I'm not sure if this 5 implementations was actually at that time, but nowadays there's definitely more than 5, and Akka Streams is one of them. So what are these Reactive Streams? Reactive Streams is an initiative to provide a standard for asynchronous bloody. So let's kind of zoom in on the important parts in this mouthful. Stream processing, what does this mean? Well, you have something that emits elements, possibly infinitely, forever, like compared to a collection, which usually has an end. And then you have some processing that happens on these elements, and then somewhere you want to kind of have an endpoint where they are consumed. So these concepts here, the source, flow, and sink, are actually Akka Streams terms. It's not in the Reactive Streams. So I'm kind of sneaking it in here to make it easier to understand later when we get to Akka Streams. So we have elements flowing through this stream, right? It could be events from sensors, IoT stuff, right? You could have all your rooms at home have a heat sensor, and those will stream heat temperature measurements every minute, right? That would be potentially infinite stream, like until the end of time or device breaks. And then you would like to, I don't know, aggregate those maybe, get an average over the last hour and make decisions based on that, right? So the next interesting part is asynchronous. And this means a few different things in different contexts. Maybe you have heard about Node, and also Akka does asynchronous in one sense of the word, where it means that you have very few threads and you never block stuff. You react on things happening. You don't kind of use a lock to wait for another thread to complete an operation, but instead you have some kind of framework toolkit that allows you to schedule processing without blocking threads, and basically just using so many threads as you have cores in your computer. In Reactive Streams, it means that every kind of stage in a stream of the processing part can be on a different thread, right? So there can be an asynchronous boundary between every of these. So the source can generate elements or pick up elements from a database or get them from a sensor and do some kind of processing. And it hands them over to the next step, and the next step can do processing, and that doesn't really kind of stop the thread, the source thread, from executing, or right? And the coolest thing is the non-blocking part, right? So if we have an asynchronous boundary like this, and we have a faster producer than we have consumer, right? So we have a producer which gives us 10 messages per second. And then in the far end, we have something that consumes the events, but it can only accept one at a time, one at a second, right? So this is a problem. We have a higher inflow than we can handle. So one option is to do nothing, right? Which means that there must be a buffer somewhere. And if we do nothing, then this buffer will over time fill up. And you will get grumpy cat out of memory JVM crash. Or we can decide to throw away elements, right? So we have a bounded buffer on the slower side, and we say, like, we can fit 10 elements in here, actually 6 elements. And if this buffer is full when we get a new element, we just throw it away. We put it in the paper bin, right? This would mean that for source to be sure that an element was processed and not just deleted, we would need to have some kind of ACK or verification that the stuff was actually processed. And then it would have to resend. And if we're already, sending more elements in than the other end can accept, how does resending then improve that situation, right? So that's not very good. So instead, what Reactive Streams has kind of, the really cool thing about it is that we have like a back pressure channel, which is also asynchronous. So from the far end of the stream, there is some way of communicating across the boundary, saying, hey, I can process 2 elements because I have space for 2 elements in my buffer. And pass that on backwards. That means that flow in this processing stage in the middle can ask the source and say like, hey, I can process 2 elements because I know downstream someone has asked for those. And upstream can never be allowed to send more elements than downstream has asked for, right? So this means that downstream being slower in this case will effectively also slow down the source. Yeah, everyone got this? Perre? Great, thank you. So what Reactive Streams does then is defining this specification, and it's not meant for you guys, most of you guys, to implement. It's a library kind of interoperability specification. So what it will allow is Akka Streams and Vertex, for example, having this back pressure between technologies, even though our internal implementations are entirely different. So this is a really nice thing, that we can take different kind of streaming technologies and use them together without them knowing anything about each other, except for that they implement the Reactive Streams. And in fact, the Reactive Streams API then got part of the Java 9, so the actual kind of interfaces will be in the Java 9 release at some point. And I think also some kind of example implementations will be in the JDK. Thing is, though, that when we started building this, we realized that you as a kind of end user of these streams, you don't want to implement this yourself. Because this is the set of rules in the specification that you must fulfill. And being asynchronous means that they are also really hard to get right. So this is not something you want to do every time you're going to build something custom with this. So instead, we have created a higher level streaming API that kind of protects you from doing this the wrong way. So now we're going to get to the main act of this show, Akka Streams. So Akka Streams looks like this. I'm going to show you some Java code. And let's see. In this one, I have included some boilerplate. So except for this and the imports, which I don't show here, this is essentially a main function that you can run. This is an entire application. And if you want to look at or try out the actual complete thing, then in the slides that will be on the somewhere later on the JFocus homepage, I guess. So in the PDF, you will be able to click this link on every sample and get to the actual sources on GitHub, and you can clone those and actually run them on your computer if you want. So I'm gonna exclude this kind of boilerplate in the following samples, just to make them a bit easier to read. So we're gonna start with the most basic kind of API. We have a source, I already mentioned. A source is something that emits elements, right? A source of your data in a graph. It has 2 type parameters. The first one is what kind of thing it emits. So in this case, it emits integers. And more specifically, all the integers between 0 and 20 millions, right? So what this actual line does is defining a blueprint. We're not running a stream yet. We're just describing it. So it's a bit like defining a method. We're not actually calling it yet, right? And then we have a flow, which is a processing stage that has an input and an output, right? So it will accept data of some type and do something with it and emit data of a possibly different type. Could be the same type that it emits as well, right? So in this case, we're just doing a simple map. We're accepting integers and turning them into strings. Super simple operation. So we just take a lambda and make a stage in this flow from it. And then we have the sync. And this has one type parameter which says what it accepts. So in this case, it accepts strings. I think I can mention the kind of second type parameter also, maybe. So as you're defining this as a blueprint, as a method, you're not calling it yet. There are stuff that you want the stream to generate when you actually run it, right? Sorry, I'm doing this ahead of time a bit. So actually, we combine these three, the source with the flow and the sink, and we get a runnable graph. It's still not running. It's still a blueprint. So it's like these three stages connected. And we have drawn the blueprint on paper. And then we actually run and build it. So that's a separate step. And the whole runnable graph and the stages, they're immutable. So this you can do over and over again. So we can start however many numbers of instances of this stream we want by doing this runnable run, right? And when this happens, there can be stuff that we want to come out. So in this case, the sync will give us a completion stage that will complete whenever the stream completes, because we might want to side effect, for example, on stream completion. So if we have a source that actually have an end, like in this case with the 20 million, when it reaches the 20 millionth element, then that will be the end of the stream, right? And when that element has kind of passed throughout the stream will complete. And that will complete this completion stage. So that is that's kind of the last type parameter on all of these. We call them materialized value. Okay. So the types align, and if we try to combine stages that can't fit together, so in this case we have the source of integers, and we can only feed it into a flow that accepts integers, right? And when we combine it with the flow, we actually get a new source, which is a source of strings. So they compose, right? And a source of strings, we can only feed into a flow that accepts strings or a sink that accepts strings. So if we would make some crazy stuff and try to fit them together, something that doesn't make sense, then we will get a compile error. So this is like a fully typed streaming API. And so I'm a Scala guy. I'm going to have Scala samples for everything, but I'm not really going to go through them. This is how it looks in Scala. So a little bit less kind of verbose. Of course, if we have this kind of a simple flow, we don't want to kind of make many lines of stuff. It's a super simple thing. So we can also do it through like a, what do you call those APIs? A Fluent API, right? So we create the source, and then on the source we can say map, and we can give it a lambda. And then we get a new source, and on that we can say run.
One question. The
Yep.
completable future you had on the previous slide,
Yeah.
is that the JDK completable
Yeah.
future or completion stage? I mean, it's not some Akka class that happens to have the same name.
So implementation, it doesn't matter to you, but interface is the JDK one, yeah.
Okay, thanks.
And the same in Scala. So simple stuff becomes really, really simple. Complicated stuff becomes possible, I would say, with this API. Let's look at a more interesting thing, because, I don't know, mapping numbers into strings isn't maybe so useful. So we're going to throw in some HTTP in here to spice it up a bit. So this is Akka HTTP, by the way. So it's our HTTP server built on top of Akka, which you can use. We have a source which does unfold. You don't have to kind of, if you're not comfortable with what unfold would do here, because it's a very functional thing I'm doing, I'm not sure we have to go into it, but it will actually generate long numbers. For every time you ask it for a new, it will give you a +1 long number up until it wraps over, and then we'll go backwards from minus values, but then we will have to wait a really long while. So that is the unfold. We start from 0, and then for every time downstream asks for an element, we will add 1 to the current state. And then we turn those numbers into a string, and we put it in a byte string. And a byte string is a Akka type, which is for arrays of bytes, but it's immutable. So arrays of bytes which we can safely share across threads without having any locks or synchronization around it. So this is a stream of byte strings, and every chunk then will contain a UTF string with a number in. Right? And it will continue forever. And then we have the HTTP API, so it's like a declarative routing API. So we say that when there is a request to the path numbers, and it's a GET request, then we will complete that request with this response. And the actual body of the response will be this stream of numbers. So we just give it the content type of text plain UTF-8 and the stream of numbers. So this is actually then numbers as a service. And we bind it to some host and port. So this is the, except for the boilerplate I showed you before, this is the entire server. It's like, I don't know, 50 lines of Java code to make an infinitely streaming Java HTTP endpoint. Really nice. This is how it looks in Scala. A little bit simpler, but not a big difference. So let's take a little step to the side and talk about TCP. So with TCP, we actually also have back pressure because we have the moving window, right? So on each side of a connection, we have buffers. We have the send buffer and the receive buffer. And there are these little trucks that run through the cables. You might not, if you cut open the cable, you will see the small trucks coming out, trust me. But you don't want to do that because then you have no internet. So you just have to trust me on this one. And these little trucks, they go through the buffer and they go all the way to the other end. And if the other end has a process which doesn't kind of eat this element out of the buffer, that will make the moving windows stop from moving, right? So we actually will fill up the send buffer as well. And the send buffer being full will back pressure into through the TCP connector in Akka Streams and through the HTTP server and all the way back to the source. So if the far end can only receive 1 number per minute, this will back pressure all the way over the network into the server and make our numbers source not generate more numbers than 1 per minute. Right? Without us having to do basically anything about this kind of low-level stuff. It's just magic. Really cool. So let's look at another sample that is maybe more useful. Actually, this was a blog article by a guy called Colin Breck. Came up Sunday, I think. Really good blog article about why Akka Streams makes sense. I think he might be working at Tesla, so that is like extra cool. So also go read the blog article, it's great. So here we're gonna stream stuff over WebSockets. So we have full WebSocket support in Akka HTTP together with Akka Streams. And a WebSocket, right, it's basically like a TCP connection, but you start out with HTTP and then you get like a two-way stream to the browser. Right? So we have modeled that as a flow. So you see up here, flow from message, incoming message, to outgoing message. So we have incoming messages and outgoing messages. And those can be detached, but kind of often they're actually more like a request, an inner request response of some kind. Like you post data and you get an ACK maybe, or you post a few data, like in this sample, and then you get an ACK. So it takes a flow of message to message. So we're going to create a flow of message, and a message can also be a stream in itself. So this is a complication of the WebSocket standard, that when we have the WebSocket up and running, then there is a flow of messages through it. But a message in this flow can also be split up in multiple smaller parts. So it can also be a kind of a substream inside of the WebSocket. So to model this, we have different types of, can also be text or binary, but in this case we only care about text. And we will have to kind of run this inner stream. So we're going to fold it, which means that we start with a value. This is a bit like the unfold thing. We start with an empty string, and then for every element in this substream, we will concatenate it. So in the end, when this substream inside of the WebSocket reaches an end, we will have a full string that we can pass into like the next step of the logic in this stream. A little bit tricksy, but nothing super hard. We hope to make some kind of clever hiding stuff around this, but it's not in Akka HTTP yet. Yeah, so what we're actually collecting here is some kind of measurements. So we get a string representation of a measurement. Probably a really bad way of collecting measurements, but and we're going to write it in a database, but we don't want to hit the database for every measurement that comes in, right? Because we don't want to overwhelm the database with like, we have 1,000 clients connected with WebSockets, and they're all bombarding us with events, right? Then we don't want to hit the database once for every element that comes in. So what we do then is use one of the built-in stages in Akka Streams, and we say that group these up to 1,000 at a time, so we can do a batch insert of 1,000 instead of hitting the database every time. But we also don't want to lose elements, so if someone is producing really slowly, let's say like 1 every 10 minutes, we don't want to wait for 1,000 because then they will never reach 1,000. So then we also say either when we reach 1,000 in one chunk, in one batch, or when 1 second has passed. So we will write at least every second if there is any elements. And if they're going to hit us faster, we will group those together and we'll get a batch that we can insert. So this would kind of protect the database in one simple kind of stage. And then we have a synchronous method. So this means that we have a database which has a method, or not a database, but maybe like a database access object of some kind, or repository maybe. And the method actually then takes a list of strings, and when it has written those to the database, it will return a completion stage of those strings, right? So it doesn't block. This method will return right away, but we get a completion stage that will be completed when a database has been written, right? So this is the whole async thing. So we include that kind of call in the stream, and the first parameter, number 5, is how many of these can happen at the same time. So we allow up to 5 concurrent of these writes, and if there is if we reach 5, then we will back pressure. So then we won't accept any elements over the wire. And then when we get the answer back, the map async then takes the result. When it arrives, the completion stage, when it completes, that value will enter the stream. So that is what the map async does. It takes a function that returns a completion stage, and the thing inside of the completion stage will end up in the stream. So then we take the last element and send back to the client. So we tell it, this is the latest one I wrote. I wrote the chunk, but this is the latest, the highest offset or whatever. And this is how it will look in Scala. Also pretty much the same, not a big difference. Yeah. What if you get an exception from the database? So in this case, it will fail the stream because the completion stage will either complete with a success or a failure, right? And we don't have any handling here to say, like, if there is an exception due to something else. There is tools for that also in Akka Streams. But in general, that might be a good thing, right? Because if you have a client that is pushing data and the database starts failing, you might not want to just keep trying. You might want to deal with it in some other way. Okay, let's talk about Pancakes. Pancakes. So these are a few of my colleagues in the team. There's one missing. There's two missing. I'm missing, but I'm here. And then there is a German guy who isn't in there. So this is Roland Kuhn. He wrote the Reactive Design Patterns book, and he was the tech lead for the Akka team for a bunch of years. And this is Patrik Nordvall, Swedish guy from Stockholm, who is the current tech lead of the Akka team. And they both like Pancakes very much. So we're going to talk about how they make pancakes. Yeah, let's set the stage a bit. We have a source of batter, like the pancake sauce, cream, whatever. And we have like scoops of it coming here over the stream. And we have a frying pan, and the frying pan will process those scoops into pancakes. And then in the other end, we have this hungry nom 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 sink who will eat the pancakes. Right? So Roland, he likes pipelines. So what he's going to do is he's going to have one frying pan where he fries one side of the pancake. And then he turns it over into the next pancake. So then he has the first pancake free, and he could put some more batter in it while the other side of the pancake is frying, right? So it's like a two-step thing. This kind of a pipeline is good if things are not kind of parallelizable in themselves. It's more of a sequential step of things that you need to apply to a problem, right? And it's mostly good also if the steps takes the same time, pretty much. Because if you have one step that takes longer time, let's say the frying the second side takes twice the amount of time that the first side would take, then you would have this, back pressure problem. But if you have a few steps that take the exact same time or around-ish, then you will actually get a nice flow where a little thing is done at a time. And of course, there's like an asynchronous boundary here. So you can fry something in this pan while this pan is also frying something. So that is the kind of analogy. This would look like this if you would write it in Java code. So you would have the scoop of batter, and then you would have the half-cooked pancake that kind of goes in between the frying pans. And the asynchronous boundaries in Akka Streams aren't actually inserted automatically, because pretty early on we realized that in most cases that's not what you want to do, because passing an asynchronous boundary is kind of expensive for many problems. Right? So we have seen this in the parallel collections in Scala, which someone wrote a couple of versions ago, and no one actually uses them pretty much. It's very uncommon to see them used. And I would argue for the same thing a bit about the stream stuff in Java 8, that there isn't so many problems that is this kind of map-reduce thing that fits in a collection that will be faster, that will be very much faster by just randomly splitting it up over threads. So a much more common thing is that you have a business problem that is parallelizable, or kind of you can split it up into asynchronous steps, but you need to know about the problem. So this is why you will explicitly have to insert these asynchronous boundaries. So each of these asynchronous islands, would actually then run on top of an actor. You don't see this. This is kind of the internal workings. So it's an interpreted thing where each step will run inside an actor, and the asynchronous boundaries are passed as messages between them. And to optimize this, we also have buffers in between. So upstream will actually, by default, ask for 16 elements to get 16 elements to pass the asynchronous boundary rather than one at a time, just because of this kind of cost. But you can also tune this, so you can actually tune it down to one element per send between these islands. Okay, the same in Scala, pretty much the same. So Patrick, kudos, who actually, after getting home from Canada Monday evening, got to the kitchen and made pancakes and took a picture for me so I could have in this presentation. So Patrick, he likes parallel stuff. So he's instead going to use his 2 frying pans at the same time. So he's going to put a scoop of batter in one and in another, and he's going to fry them and turn them in parallel, right? So that pretty much means that he has some kind of a balancing thing, because if this one is empty, he will put batter in it, and if this one is empty, he'll put batter in it, and if both are empty, then he will choose by round robin, I don't know. And then on the other side, he kind of merges the produced pancakes onto one plate so that he can feed it or eat it themselves. Feed his kids, I'm going to guess. Right? So when is this useful? Well, when the ordering isn't important, because you can't guarantee any ordering between the pancakes. So the first one you put in isn't necessarily the first one that comes out, right? But one really good thing with it is that it's easily scalable. So if you have 8 pans, you can just fry 8 pancakes at the same time. So if you have 8 cores, you can just, scale this up, which is much harder with, like, the pipelining thing, I guess. So this is more like the collections, the streams concurrency thing, right? We kind of map reduce. And this will look like this. And now we're seeing a more complicated API, which is called the graphDSL. And the graphDSL allows us to build streams that have cycles, for example, or that have multiple legs. So Akka Streams actually allow you to build arbitrary graphs. So it's not only even directed graphs, sort of, but you can have cycles, no problems. It's complicated, but you can do that. And to allow us to create this, we have this graphDSL. And I personally don't like the Java side so much because it gets so chatty. So let's look at the Scala API instead, because that's kind of cool. So I think this kind of self-explanatory, not exactly how we have implemented it to work like that. But I mean, if you look at the actual flow of stuff, it is kind of obvious, right? And again, we have to explicitly say the pancakes, the pans are asynchronous islands so that they will run not in the same thread or actor. So, and then we could actually have them come together. There will be fighting in the kitchen, but we could make them do this together, and they could actually combine their 2 approaches to it. So we could actually have 2 sets of pipelines that run in parallel. So we have kind of a worker pool, and each worker is a set of stages. I'm not going to show you code for this, but this is all actually in the Akka Streams documentation. So there is samples for Java and Scala, and just pancakes in the manual, yes. So out of the box, Akka Streams comes with this set of stages. A shitload, if you pardon my French. So as they are composable, quite a bunch of things you want to do with a stream is possible by combining 2 or 3 of them. And also a few of these stages are actually combinations of other built-in stages. So what if you want to connect to dogs with a cucumber instead? Yeah, I don't know. Sorry. Well, we have this community initiative thing, which is called alpaca, which is then a wordplay on the animal and Akka, of course. And it's a community for connectors. So it's sinks and sources that connect to different technologies that we don't want to include in the core. So right now, built into Akka, we have some like basic file I/O Java Streams interrupt both the old Java Streams and the new Java Streams. The Reactive Streams connector part where we can connect different implementations, and we have connectors for actors, and we have TCP stuff, so you can actually build your own socket-level streaming stuff. And then in this alpaca project, we have a bunch of connectors to different things, and I would say the most pressing things that people are most interested in is the stuff that is in here already. So the files, for example, we have a connector that tails a file, so you will get new stuff written to the file streamed over the stream, for example. So you can write your own kind of Unix tail-f. FTP connector to stream files from an FTP server. Kafka and Cassandra is probably like the biggest ones, right? Because those are the main buzzwords in the IT business right now. Everyone wants to stream stuff from Kafka or to Kafka. And then we have a few incoming. So these are open pull requests right now. HBase, MongoDB, AVS Lambda. So take data in a stream and pass it to a AVS Lambda function. And the result goes back into the stream, basically. Super nice. And all of these, you can just combine them. So you can use the Akka HTTP server, and you can stream stuff from Cassandra or MQTT, your RabbitMQ server. I don't know, whatever you can think of. Super simple. Yeah, but I'm such a unique snowflake, and my problem, I'm building this thing that no one else has ever thought about. And this is my startup, and you're gonna be amazed when I present it, and I'm gonna be a millionaire. Well, we have stuff for that guy too. So the most low level of this kind of the Akka Streams APIs is the graphstage API. It allows you to custom build a stage that is a sink or a source or a flow yourself to connect to, for example, a legacy, something that you have, or to a database, a thing that isn't easy to connect to with the existing stuff. I'm gonna use the Scala source instead of the Java one because it's a bit more concise, but the APIs is pretty much the same. So what you do is you define a graph stage, and it has a shape, and the shape defines if it's an input and output or a flow, and what kind of types that go over the flow. So this part is the kind of blueprint. It's immutable. And then we have the input and the output in this case because it's a flow, and those have the types of the input and the output. And then we have the thing that is actually created when we run. So when you actually run or materialize a stage, this is what will get called, and it will create an instance of graphstage logic where you can have mutable state. And this is entirely kind of guaranteed that you can mutate stuff. It will be executed on different threads, but Akka guarantees that you don't have to care about concurrency with your state inside of this. And for each input and output, we can set handlers. So in this case, we set a handler for the output, and one at a time, we will get a pull from downstream, which means that downstream is ready for element to be pushed downstream. And in this case, we're doing a simple map, so we're just gonna pass the pull upwards in the stream. So upstream, we tell, hey, I want an element. And when upstream has an element that it pushes, we will get a callback to this, on push. And on push, we can grab the element from the input, and we can push it downstream. And here also, we apply the function that we took to the constructor. So this is all there is pretty much to the actual map stage if you look at the actual implementation inside of Akka Streams. Of course, if you do more complicated things, it will be a bit more complicated. But again, simple stuff is simple, pretty much simple, and complicated stuff is possible. Kind of a good motto. Yeah, so what I didn't quite mention is that this is an entirely local abstraction. There is no distribution in it at all. There is these guys at Intel who are trying to take a stream blueprint and just materialize and run it across a cluster. It's a project called Gear Pump. Pretty cool. I'm not sure how far they have come with that, or like if you can actually run it yet, or anything like that. We try to help them whenever they have problems. But a pretty cool thing is that this fits very well. So Akka Streams are local, but they fit really well together with actors. So if you, for example, have a huge amount of elements that you need to process out of a Kafka server, Kafka cluster, then you could use the cluster tools in Akka to make sure that you have one stream processor per core, per node in your cluster, and then you use the consumer groups, I think, in Kafka, to make sure that you get like just a subset of the elements, and that you are saving enough set for just that subset. Then when one node crashes, you can use the cluster tools to have it start up on a different node, for example. So it fits really well together. You can achieve like resiliency and all that, even though it's a local abstraction. Yeah, we're 6 people who are employed at Lightbend who work with Akka. We have about 200 active contributors in the community, very active community. And I mean, the alpaca project is essentially just community. So we have written a few stages to set examples, but most of them are actually people who are filling their own needs, sort of. So this is really cool. Very well functioning open source community, I think. You can find help on the mailing list, and we have the public chat rooms where you can come talk to us. We have marked up easy to contribute tickets if someone wants to contribute to help out with Akka. I think that was it. You have any questions? Perre? No? Crystal clear?
There's one over there.
Yeah, so I think I know your answer, but like, what do you prefer, this or RX?
So RX.
Or like, what are the advantages and disadvantages of either?
So I think we fulfill a bit different needs. I would say I would probably not use Akka Streams to define a UI, but I might use RX for that because it fits very well. I think this has some kind of pros when we're talking more back-end processing, streaming things. And also, kind of, as soon as you want to make custom things, that will be much, much harder with RX. It's my impression, at least. So, of course, I'm biased, but I mean, we have taken the decision to have interpreted streams where we actually have a safety net around them. And I'm not sure if any of the other Reactive Streams implementations does anything like that. So if you're going to misbehave, if you're going to write a custom stage and you're pulling even though you didn't, you pulled twice without having gotten an element in between, we will help you out and tell you that you did it wrong, rather than give you weird, it will continue working, but you didn't know that something went wrong, which is a much worse case. Yeah. Did that answer your question? Vaguely?
Kind of.
Okay. Yeah.
Do you have an example of handling exceptions?
Do I have an example of handling exceptions? Not readily available here, but I would say there is like 2 ways to do it. There's 3 ways to do it. Three ways. So the first way is a stage that is called recover. And recover will let you, when there is a failure in the stream, so an exception that you don't catch, it will fail the stream. And recover will make the stream continue with an alternative. So you can both recover with a single element, or you can recover with a new stream, sort of. So if you have a source section that fails, you can produce a new source section. Then some stages have supervision strategies, like the actors have. So for some stages, you can say, if there is an exception, ignore it and resume. If there is an exception, fail the stream. If there is an exception, stop the stream, but not as a failure. And then the third way is to model it in your stream. So then you would actually encapsulate your exceptions as stream elements. So like the try type in Scala, or Java slang also has that, I think. So you would actually model a try to do something, which could be a successful value or a failed try to make that value with the exception. So you will have that as an object instead of a flow control thing. And then you can also handle it throughout your stream however you want. You might split off all those into a separate branch where you send them to a log file with the failures.
Okay, I think we're at the wrap up, and thank you, Johan, for this session and talk.